I want to start with something you use every day without questioning. Distance. The distance from your hand to the wall across the room. The distance from your home to your workplace. The distance from Earth to the moon, from the sun to the nearest star, from the Milky Way to Andromeda. Distance seems like the most straightforward concept in physics. It is a measurement, a number with units, something you can verify with a ruler or a radar or a telescope. It is not the kind of thing that admits of doubt. I want to show you that distance, in the precise sense that modern physics understands it, is not what you think it is, not approximately different from what you think. Not different at extreme velocities or extreme scales in ways that can be safely ignored for everyday purposes. Different in a way that is fundamental, that applies to every measurement you have ever made, that reveals something about the structure of space and time, that dismantles the intuition you were born with and replaces it with something stranger and more precise. The distance between two events in space-time is not a single number that all observers agree on. It is a quantity that depends on the observer. Two observers moving relative to each other will measure different distances between the same 2 points. Both measurements are correct. There is no privileged observer whose measurement is the true one. Distance is observer-dependent, frame-dependent, relative. This is not a philosophical position. It is a theorem of special relativity confirmed by every experiment that has tested the theory for more than a century. It has practical consequences that engineers building GPS satellites and particle physicists designing accelerators must account for. And it has deep implications for what space actually is, implications that go beyond the relativistic corrections and reach into the nature of geometry itself. I want to take you through the full argument from the Michelson-Morley experiment that shattered the 19th century picture of space, through Einstein's two postulates and their immediate consequences, through length contraction and the relativity of simultaneity, through the four-dimensional space-time interval that replaces the three-dimensional distance as the invariant quantity, and finally to what all of this means for the reality of space, the nature of the universe, and the question of what it means to say two things are far apart. Let me start with what physicists believed about space before Einstein, because the 19th century picture was coherent, beautiful, and completely wrong. In the late 19th century, physicists understood space as Newton had described it, an absolute, fixed, three-dimensional container in which matter and energy existed and moved. Space was the stage. Matter was the actors. The stage existed independently of the actors. Its geometry was Euclidean, flat, the same everywhere. Distances were absolute. The distance between 2 points in space was a definite number that all observers would agree on, independent of their motion. This Newtonian picture had one unresolved puzzle. Light was known to be a wave, discovered definitively by Thomas Young's double-slit experiment in 1801 and described mathematically by Maxwell's equations in 1865. But waves require a medium. Sound waves propagate through air. Water waves propagate through water. What did light waves propagate through? The answer that 19th century physicists converged on was the luminiferous ether, a medium that filled all of space through which light propagated. The ether was the medium of light, the substrate of space itself. Its properties were extraordinary. It had to be rigid enough to support the high-frequency oscillations of light, yet so thin and frictionless that planets could move through it without measurable resistance. Its rigidity had to be sufficient to propagate oscillations at the speed of light, approximately 300,000 kilometers per second. For comparison, the rigidity needed for that propagation speed is many orders of magnitude greater than the stiffest known solid materials. The ether was, in mechanical terms, more rigid than steel by an enormous factor, yet completely undetectable by any mechanical measurement. This was already uncomfortable. If the ether existed and filled all of space, then the speed of light should depend on the motion of the observer through the ether. An observer moving toward a light source should measure a higher speed of light than an observer at rest, just as a swimmer moving toward oncoming waves encounters them more frequently than a stationary swimmer. The Earth, in its orbit around the Sun, moves through the ether at approximately 30 kilometers per second. This motion should produce a measurable difference in the speed of light measured in different directions of order v over c, approximately 1 part in 10,000. In 1887, Albert Michelson and Edward Morley performed the most famous null result in the history of physics at what is now Case Western Reserve University in Cleveland, Ohio. They built an interferometer on a stone slab floating on liquid mercury to isolate it from vibrations. The interferometer split a light beam into 2 perpendicular paths, reflected each path off mirrors, and recombined them. If the speed of light differed in the 2 directions due to Earth's motion through the ether, the recombined beams would show a specific interference pattern, a fringe shift when the interferometer was rotated. Michelson and Morley calculated that their instrument was sensitive enough to detect a fringe shift of 0.4 fringe if Earth's orbital velocity produced the expected ether wind. They observed a shift of at most 0.01 fringe, consistent with 0. The speed of light was the same in every direction to the precision of their instrument, which was more than 40 times what was required to detect the expected effect. The Michelson-Morley experiment was a catastrophe for the ether theory. Various attempts were made to save it. George Fitzgerald in 1889 and Hendrik Lorentz in 1892 independently proposed that objects moving through the ether contract in the direction of motion by exactly the factor needed to make the ether undetectable. The contraction factor was 1 over gamma, precisely the Lorentz contraction factor. This was ad hoc, invented specifically to explain the null result with no independent motivation. But it contained the seed of something deeper. Lorentz and Henri Poincaré developed the mathematics of the transformations that leave Maxwell's equations invariant, what we now call Lorentz transformations. They derived time dilation and length contraction mathematically, but they still believed in the ether. The Lorentz transformations were, in their view, describing the effect of motion through the ether on physical objects. The contraction was real. The time dilation was real. But the ether was still real, just undetectable. Einstein's approach in 1905 was different and more radical. Instead of trying to explain why the ether could not be detected, he proposed that it did not exist. He took the Michelson-Morley result as a fundamental fact. The speed of light is the same for all observers, regardless of their motion. Not as a derived consequence of some deeper theory, but as a postulate, a fundamental axiom of physics, combined with the other postulate that the laws of physics are the same in all inertial frames. This single assumption generated all of special relativity. The consequences followed with mathematical necessity. If the speed of light is the same for all observers, and if 2 observers are moving relative to each other, then their measurements of space and time must differ. There is no way to reconcile a constant speed of light with absolute space and absolute time. One of them must be sacrificed. Einstein sacrificed both. Let me derive the most important consequence directly. Consider 2 observers, one stationary and one moving at velocity v. Both observe a light pulse travel from one point to another. Both must measure the same speed for the light pulse, because the speed of light is the same for all observers. But if the light pulse takes a longer path in the reference frame of the moving observer, it must take more time for the moving observer, since it travels at the same speed over a longer path. This is time dilation. Similarly, consider the distance between 2 points as measured by a stationary and a moving observer. The stationary observer measures a specific distance. The moving observer, who is in motion along the direction between the 2 points, measures a shorter distance. The two measurements are related by the Lorentz factor gamma, which equals 1 divided by the square root of 1 minus v squared over c squared. When v equals 0, gamma equals 1, and the measurements agree. When v approaches c, gamma approaches infinity, and the measured distance approaches 0. This is length contraction. An object moving at velocity v relative to an observer appears contracted in the direction of motion by a factor of 1 over gamma compared to its rest length. An observer moving at velocity v relative to a stationary object measures the object to be contracted by the same factor. And here is the crucial point. Both measurements are correct. The stationary observer measures the true rest length of the object. The moving observer measures a shorter length. These are not errors or illusions or artifacts of measurement. They are the actual distances in their respective reference frames. There is no single true length. Length is observer dependent. This is not a subtle effect visible only at velocities close to the speed of light. It is a feature of every measurement of distance ever made. When you measure the distance from your hand to the wall, you are measuring the distance in your reference frame. A physicist in a rocket moving past you at a significant fraction of the speed of light measures a different distance. Both are correct. The concept of a single true distance, independent of the observer, does not exist. The Lorentz factor at everyday velocities is so close to 1 that the difference between the contracted and uncontracted lengths is far below any measurable threshold. A car moving at 100 kilometers per hour has a Lorentz factor of 1 plus 8 times 10 to the minus 15, meaning the contraction is 15 parts per quadrillion, completely undetectable in practice, but real in principle, and at velocities approaching the speed of light, dramatically real in practice. If the speed of light is the same for all observers, and if two observers are moving relative to each other, then their measurements of space and time must differ. There is no way to reconcile a constant speed of light with absolute space and absolute time. One of them must be sacrificed. Einstein sacrificed both. Let me derive the most important consequence more carefully. I want to show you, step by step, why the constancy of the speed of light forces length contraction. Imagine a light clock, a device that measures time by bouncing a photon between two mirrors. The mirrors are separated by a distance L. The photon bounces back and forth, each round trip taking a time of 2L over c. This is the tick of the clock. The clock is stationary in its own frame. Now put the clock on a spaceship moving at velocity v relative to an observer on Earth. The clock is oriented perpendicular to the direction of motion, so the mirror separation L is unaffected by the motion. But from the Earth observer's perspective, the photon does not just bounce up and down, it traces a zigzag path because the mirrors are moving horizontally. As the photon moves vertically, the photon travels a longer path than 2L. Since the photon moves at c in the Earth frame, and the path length is longer, each tick takes longer in the Earth frame than in the spaceship frame. The clock on the spaceship runs slow. This is time dilation. The time between ticks in the Earth frame is 2L over c times gamma, where gamma equals 1 over the square root of 1 minus v squared over c squared. Now rotate the clock so it is oriented parallel to the direction of motion. A naive expectation would be that the clock runs at the same rate as before since only the orientation changed, but it does not. If the clock ran at a different rate depending on orientation, a physical effect would distinguish different orientations, violating the isotropy of space. The clock must run at the same rate regardless of orientation. For the parallel clock to run at the same rate as the perpendicular clock, despite the photon having to chase the moving mirror in one direction and be chased by it in the other, the length of the clock in the direction of motion must be shortened by a factor of 1 over gamma. This is length contraction. The length of an object in the direction of motion is contracted by the factor 1 over gamma. This is not a consequence of physical forces pushing the object together. It is a consequence of the geometry of space-time. The object's rest length, measured in its own frame, is unchanged. The contracted length is the length measured by an observer in motion relative to the object. Both are real measurements. Neither is an illusion. But only the rest length is a property of the object. The measured length depends on the observer. The Lorentz factor gamma, 1 divided by the square root of 1 minus v squared over c squared, is the key quantity. At v equals 0, gamma equals 1, and no contraction occurs. At v equals 0, 866c, gamma equals 2, and objects are contracted to half their rest length. At v equals 0, 99c, gamma equals approximately 7, and objects are contracted to 1/7. At v approaching c, gamma approaches infinity, and lengths approach 0. For a human walking at 5 kilometers per hour, gamma equals approximately 1 plus 10 to the minus 17. The contraction is 10 to the minus 17 of the rest length, roughly 1/10,000,000th of a proton diameter, completely undetectable. But at 0, 999c, gamma equals approximately 22. An object 100 meters long in its rest frame would be measured as approximately 4.5 meters long by a stationary observer. The contraction is dramatic and measurable. Muons created in cosmic ray interactions in the upper atmosphere provide the most directly observable demonstration. Muons have a rest frame lifetime of approximately 2.2 microseconds. They are created at altitudes of approximately 15 kilometers, traveling toward the ground at velocities close to the speed of light. At 99.7% of c, the Lorentz factor is approximately 13. The 15-kilometer distance from creation to detection is contracted in the muon's frame to approximately 1.2 kilometers. The muon crosses this contracted distance in approximately 4 microseconds, well within its lifetime. In the Earth frame, the muon's internal clock runs slow by a factor of 13, so the muon takes approximately 50 microseconds of Earth time to cross the 15 kilometers, but only ages by 50 divided by 13, approximately 4 microseconds, before reaching the ground. Both descriptions are correct. Length contraction from the muon's perspective, time dilation from Earth's perspective, both predict that the muon reaches the ground before decaying. Both are confirmed by observation. The distance from the upper atmosphere to the ground is 15 kilometers in Earth's frame and 1.2 kilometers in the muon's frame. Both are correct. Neither is the true distance. Muons created in cosmic ray interactions in the upper atmosphere provide the most commonly cited demonstration. Muons have a rest frame lifetime of approximately 2.2 microseconds. They are created at altitudes of approximately 15 kilometers and travel toward the ground at velocities close to the speed of light. At sea, a muon would travel only 660 meters in 2.2 microseconds, far less than the 15 kilometers to the ground. Yet muons are detected at ground level in abundance. The resolution is length contraction. In the muon's frame, the 15-kilometer distance is contracted to approximately 660 meters by the Lorentz factor of the muon's velocity. The muon travels this contracted distance in 2.2 microseconds and arrives at the ground before decaying. In the Earth's frame, the same physics is described by time dilation. The muon's internal clock runs slow due to its motion, so it takes much longer than 2.2 microseconds in Earth's frame to decay. Both descriptions are correct. Both involve a modification of the naive expectation that distances and times are absolute. Now I want to take you to the deeper structure that replaces the old concept of distance, because special relativity does not just say distance is relative. It says there is a different quantity, the space-time interval, that is not relative. And understanding the space-time interval changes everything. In three-dimensional Newtonian space, the distance between 2 points is given by the Pythagorean theorem. D squared equals delta x squared plus delta y squared plus delta z squared. This distance is invariant under rotations. If you rotate your coordinate system, the components delta x, delta y, delta z all change, but the combination d squared does not. Distance is the invariant quantity of three-dimensional Euclidean geometry. To understand why this is invariant, consider what rotation does. It changes how you decompose the vector between 2 points into components. If you are measuring the distance between two cities and you orient your coordinate system with x pointing north and y pointing east, you get specific values of delta x and delta y. If you rotate the coordinate system so x points northeast, you get different values. But the Pythagorean distance, the square root of delta x squared plus delta y squared, is the same in both cases. Rotation mixes the components but preserves the total. In four-dimensional space-time, there is an analogous invariant. The space-time interval squared is defined as s squared equals minus c squared delta t squared plus delta x squared plus delta y squared plus delta z squared. The crucial difference from the Pythagorean theorem is the minus sign in front of the time component. This interval is invariant under Lorentz transformations, the space-time equivalent of rotation. Different observers moving relative to each other will assign different values to delta t, delta x, delta y, and delta z for the same pair of events. But they all agree on s squared. Why the minus sign? The minus sign reflects the fundamental asymmetry between space and time in the structure of space-time. In space, all directions are equivalent. You can rotate freely among x, y, and z, but you cannot rotate into the time direction in the same way. Time is different from space in a specific mathematical sense. The metric has one negative signature. This is what distinguishes space-time from four-dimensional Euclidean space, and it is what makes the causal structure, the division into past, present, and future, possible. The minus sign has profound consequences. For two events that are separated in space and time, s squared can be positive, negative, or zero. When s squared is positive, the spatial separation dominates. The two events are space-like separated. The spatial distance is larger than c times the time difference. No material object can be present at both events because that would require traveling faster than light. Different observers disagree about the time ordering of space-like separated events. Some will say A happened before B. Others will say B happened before A. This is the relativity of simultaneity. When s squared is negative, the temporal separation dominates. The two events are time-like separated. A material object moving slower than light can be present at both events. All observers agree that the event with the earlier time coordinate occurred first. The magnitude of the interval, the square root of the absolute value of s squared divided by c squared, is the proper time, the time measured by a clock that travels between the two events. The proper time is the deepest invariant of special relativity. It is the time actually experienced by an observer who moves between two events. Different paths through space-time between the same two events have different proper times because the integral of the interval element along the path differs. This is the twin paradox. Twins who separate at one event and reunite at another. taking different paths through space-time, age differently. The twin who travels faster takes a path with a shorter proper time and ages less. This is not an illusion or an apparent effect. When the twins reunite, the age difference is real and permanent. When s squared is 0, the two events are light-like separated. They can be connected by a light ray. A photon emitted at one event can arrive at the other. The space-time interval for a photon's world line is always 0. This means that in a very precise sense, from the photon's perspective, no time passes and no distance is traveled. The photon emitted from Andromeda 537 million years ago in our frame travels no distance and experiences no time in its own frame. It is emitted and absorbed instantaneously with 0 interval between the two events in the frame defined by the photon's own propagation. This is the most striking consequence of the 0 space-time interval for light. The photon that reaches your eye tonight from Andromeda left 2.537 million years ago in your frame. In the photon's frame, the emission and absorption are simultaneous. The photon does not experience a journey. It is at both places at the same time, in the sense that the space-time interval between the two events is 0. This is the precise physical content of the statement that the distance to Andromeda depends on the observer. In our frame, the distance is 2.537 million light years. In the photon's frame, the distance is 0. Both are derived from the same underlying space-time interval. The space-time interval is the truth. The specific distance is the frame-dependent shadow. This threefold classification of separation, space-like, time-like, and light-like is the fundamental causal structure of space-time. It determines which events can influence which other events. Two events with a space-like separation cannot have any causal relationship. No signal can travel between them. Two events with a time-like or light-like separation can be causally related. The earlier event can cause the later one. The causal structure is absolute. Whether two events are space-like, time-like, or light-like, separated is agreed on by all observers. Whether one event caused the other, whether a signal can travel between them, whether the time ordering can be reversed, all of these are frame-independent facts. The causal structure of space-time is the physical reality. The specific distances and time intervals are not. Let me now develop what this means for the concept of distance, because I want to be precise about the sense in which distance is an illusion. Distance is not an illusion in the sense of not existing. The measurement of distance is real. You can measure the distance from your hand to the wall, and you will get a specific number in centimeters, and that number will be consistent with the speed of light and the time it takes for a radar pulse to reflect off the wall. The measurement is real. Distance is an illusion in the sense that it is not fundamental. It is a derived quantity, a component of the full four-dimensional space-time interval, observer-dependent, frame-dependent, changing when you change your state of motion. The true invariant, the space-time interval, is four-dimensional and includes both the spatial separation and the temporal separation. Neither component alone is invariant. Only their specific combination with the minus sign for the time component is invariant. When we measure distance in everyday life, we are measuring the space-time interval in a specific limit. The limit where the time component is 0, meaning we are measuring the spatial separation between two events that are simultaneous in our frame. Simultaneous in our frame, not simultaneous in all frames. An observer in motion relative to us would not consider the two events simultaneous, so they would not be measuring the spatial separation in the same sense. They would measure a different spatial separation. This is the precise sense in which distance is frame dependent. It is the spatial component of the space-time interval, and the spatial component depends on how you slice the four-dimensional block into space and time. Think of the block universe I described in the earlier video about the permanence of the past. The four-dimensional space-time structure is the fundamental reality. Spatial distance is what you get when you slice the block with a specific spatial hypersurface, a specific three-dimensional snapshot of the universe at a specific moment. Different observers moving at different velocities make different slices. The spatial distances they measure are the dimensions of the different slices. The slices are all legitimate cross-sections of the same four-dimensional block. None is more real than the others. Now let me take you to something that extends this picture beyond special relativity into general relativity. Because in general relativity, the concept of distance becomes even more observer-dependent and even more counterintuitive. In general relativity, space-time is not flat. It is curved by the presence of matter and energy. The geometry of space-time near a massive object is different from the geometry far away. Distances in curved space-time do not follow the Pythagorean theorem. They follow the generalization of the Pythagorean theorem for curved geometries, the metric tensor. Let me explain what the metric tensor is, because it is the central object of Riemannian geometry and of general relativity. In flat Euclidean space, the distance between two infinitesimally separated points is given by ds squared equals dx squared plus dy squared plus dz squared. In curved space, the distance between two infinitesimally separated points is given by ds squared equals g ij dx I dx j, where g ij is the metric tensor, a matrix of numbers that varies from point to point in the curved space. The metric tensor encodes the local geometry at every point in flat space. G ij is the identity matrix. The metric tensor has ones on the diagonal and zeros off the diagonal. In curved space, the metric tensor is different, reflecting the curvature. The specific form of the metric tensor near a massive object is the Schwarzschild metric, discovered by Carl Schwarzschild in 1916, which gives the geometry of space-time outside a spherically symmetric mass. The Schwarzschild metric shows that both the time component and the radial distance component of the space-time metric are modified near a massive object. The time component is multiplied by a factor of 1 minus the Schwarzschild radius divided by r, where r is the distance from the center. This factor is less than 1, meaning clocks near the object run slower than clocks far away. The radial spatial component is divided by the same factor, meaning radial distances near the object are larger than in flat space. Near the Schwarzschild radius, the factors go to 0 and infinity, respectively. These modifications have practical consequences. GPS satellites orbit Earth at an altitude of about 20,200 kilometers. At this altitude, the gravitational potential is weaker than at Earth's surface. The general relativistic effect makes the satellite clocks run faster than ground clocks because they're in a weaker gravitational field, approximately 45 microseconds per day faster. But the special relativistic effect makes the satellite clocks run slower because they are moving, approximately 7 microseconds per day slower. The net effect is that satellite clocks run approximately 38 microseconds per day faster than ground clocks. 38 microseconds per day sounds small, but GPS works by measuring the time for signals to travel from satellites to the receiver and inferring position from the time differences. 38 microseconds corresponds to a distance error of approximately 11 kilometers per day if the relativistic corrections were not applied. GPS would be useless without accounting for both special and general relativistic corrections to the rate of clocks at different velocities and gravitational potentials. The modification of distances near extremely compact objects produces phenomena with no Newtonian analog. Near the event horizon of a black hole, the metric is so distorted that the radial spatial direction and the time direction effectively exchange roles. Inside the event horizon, the Schwarzschild time coordinate becomes space-like and the radial coordinate becomes time-like. The singularity at r equals 0 is not a place in space. It is a moment in time. An observer who falls into a black hole is not falling toward a place they could choose to avoid. They are falling toward a moment in their future that is as unavoidable as tomorrow. This is the most dramatic consequence of the curvature of space-time near a black hole. The geometry is so distorted that the ordinary meanings of space and time are inverted. Distance toward the singularity is not a spatial distance in any ordinary sense. It is a temporal direction. The black hole's interior is not a place. It is a time, the inevitable future of everything that falls in. There is a specific consequence of curved space-time that I want to describe because it directly illustrates the observer dependence of distance in general relativity. Consider the distance from the Earth to the Sunday. In flat space-time, this would be simply 150 million kilometers, the Euclidean distance between 2 points. But space-time near the Sun is not flat. It is curved by the Sun's gravity. In the curved space-time near the Sun, a straight line, which would be the shortest path in flat space, is not the path of shortest proper time between the Earth and the Sunday. The path of shortest proper time is a geodesic in the curved space-time, which in the case of the Earth's orbit is an ellipse in the three-dimensional spatial projection. The orbit is straight in four-dimensional space-time but curved in three-dimensional space. The distance from Earth to the Sun in the curved space-time of general relativity is not simply the Euclidean distance. It depends on the metric, which is curved by the Sun's mass. A radar signal sent from Earth to the Sun takes slightly longer than the flat space calculation would predict, because the signal follows a curved path through the curved space-time, passing through regions where the spatial metric is stretched. This Shapiro delay, predicted by Erwin Shapiro in 1964 and measured to extraordinary precision, is a direct measurement of the distortion of spatial distances near the Sunday. In general relativity, the concept of the distance between two objects depends not just on the state of motion of the observer, as in special relativity, but on the distribution of matter and energy between and around them. Distance is a relational, context-dependent, observer-dependent quantity. The notion of a single true distance between any two objects in the universe does not exist in general relativity any more than it exists in special relativity. Let me now bring all of this together into the conclusion that I think is most important, which is about the nature of space itself. Before I do, let me describe one more consequence of the relativity of distance that I think is the most practically important and the most personally significant: the implication for travel. In the standard picture, the nearest star beyond the Sun, Proxima Centauri, is 4.24 light years away. At the speed of light, it would take 4.24 years to reach it. Since nothing can travel at the speed of light, and the fastest we can realistically imagine sending a spacecraft is perhaps a significant fraction of c, the journey would take at minimum several years and more likely decades. The scale of interstellar space, even to the nearest star, seems to make human-scale interstellar travel impractical within a human lifetime. But length contraction changes this picture dramatically. A spacecraft traveling at 99% of the speed of light has a Lorentz factor of approximately 7. The 4.24 light-year distance to Proxima Centauri is contracted in the spacecraft's frame to approximately 0.6 light-years. The journey takes approximately 0.6 years, about 7 months of proper time for the traveler. Even though 4.3 years pass on Earth, a spacecraft traveling at 99.9% of C has a Lorentz factor of approximately 22. The contracted distance is approximately 0.2 light years, and the journey takes about 0.2 years, about 11 weeks of traveler's time. At 99.9999% of C, gamma is approximately 707.12. The 4.24 light-year distance contracts to approximately 0.006 light years, and the journey takes about 2 days of traveler's time. The year passes on Earth, the traveler ages 2 days. This scales to truly extraordinary distances. At a velocity of 1 minus 10 to the minus 8 times c, gamma is approximately 7,000. The 2.537 million light-year distance to Andromeda contracts to approximately 363 light-years in the traveler's frame. At this speed, the journey to Andromeda takes approximately 363 years of traveler's time. The universe on Earth ages 2.537 million years. The traveler could, in principle, cross the observable universe 46 billion light years in Earth's frame in approximately 46 years of traveler's time. If they could sustain a velocity close enough to c, they would arrive at a universe 46 billion years older, but they would have aged only 46 years. This is not magic. It is length contraction. The distances they traverse are contracted in their frame to a fraction of the distances in Earth's frame. The true invariant space-time interval along their world line is entirely in the time direction, proper time, not the spatial direction, because their world line is nearly light-like. The distance to Andromeda is not 2.537 million light years in any absolute sense. It is 2.537 million light years in our frame. In the frame of a sufficiently fast spacecraft, it is 363 light years. In a photon's frame, it is 0. All are correct. None is the truth. This is the practical consequence of the illusion of distance. Space is not a fixed background. It is a relationship between observers and events mediated by the geometry of space-time. The distances we measure are real, but they are not absolute. They are the spatial components of four-dimensional space-time intervals, sliced and projected into 3 dimensions by the particular motion and position of the observer. Space is not a fixed, pre-existing container. It is a dynamic, geometric structure that depends on matter and energy and on the state of motion of the observer. The distances within it are not absolute facts about the universe. They are relational facts about the observer and the observed. Different observers inhabit different 3-dimensional slices of the 4-dimensional block. The distances they measure are real, but they are the distances of their particular slice, not the distances of some absolute 3-dimensional reality. The 4-dimensional space-time interval is the closest thing physics has to an absolute distance. It is the quantity that all observers agree on, the invariant of Lorentz transformations, the true geometric distance in 4-dimensional space-time. But even the space-time interval is not an absolute property of 2 points in space. It is a property of 2 events, 2 points in space-time, which includes both a spatial location and a temporal coordinate. To say that 2 objects are far apart in space, one must specify at what time, in which reference frame, and with which slice of the 4-dimensional block. The statement that the Andromeda Galaxy is 2.537 million light years away is a statement about the spatial separation in our reference frame at the current cosmic epoch, in the cosmological coordinates in which the universe is approximately homogeneous and isotropic. It is a real, measurable, well-defined distance, but it is not the distance in any absolute frame-independent sense. In the reference frame of a photon emitted from Andromeda, the spatial distance to Earth is 0 because the space-time interval for a null geodesic, a light-like path, is 0. In the frame of a hypothetical observer moving at 99.9% of the speed of light toward Andromeda, the distance is contracted by a factor of more than 20 to approximately 120,000 light years. All of these are correct measurements of the distance in their respective frames. The distance from here to Andromeda is 2.537 million light years in our frame. In a photon's frame, it is 0. In a hypothetical relativistic traveler's frame, it is whatever the Lorentz contraction gives. All are correct. None is the truth. This is why distance in space is an illusion. Not because distances are not real, but because the concept of distance in space, as opposed to the space-time interval in space-time, is observer-dependent, frame-dependent, relative. It is a slice of a four-dimensional reality, and the slice depends on who is doing the slicing. The universe is four-dimensional. Space is what you get when you look at one slice of it, and the slice you see depends on where you are, when you are, and how fast you are moving. If this changed how you think about distance, about space, about what it means to say two things are far apart, tell me in the comments. Tell me whether the observer dependence of distance disturbs you or whether it opens up new ways of thinking about the universe. Tell me whether the fact that a photon traveling from Andromeda experiences 0 distance disturbs your intuition about what it means to travel across space. And subscribe if you want to keep going into the places where the physics of space-time reveals the most familiar concepts, distance, time, space, to be far stranger than they appear.